Okay, I really think we should have another subsection, whatever it is. Is it 26? Welcome to the improvised subsection on ordered symbol tables. I feel this should be broken into two parts. So this is still discussing binary search trees and dictionaries, but I want to make this an additional part so that the videos don't get too long. It turns out that the operations from the symbol table I've shown before are not all that you want, and not all that binary search trees can easily support efficiently. There's a couple of more operations, and these are the ones. One is finding the smallest or largest key in the symbol table. That's similar to priority queues, if you remember. Somewhat related is floor and ceiling. That's, well, think about, well, first of all, it is the key in the symbol table, the largest key that is just smaller than x or equal to x. So sometimes if you use floor, you just get x back, and you learn not so much, but you learned that x is in the symbol table. If x is not in the symbol table, you get the largest key that is in the symbol table but is smaller. And if you think about the ordinary floor function on real numbers to be defined as calling floor on this symbol table of all integers, which is of course infinite, and we don't want to represent it in the computer, but just as a mnemonic, you could say you take this floor function on the integers, and then it would give you exactly that, that function. And the same for ceiling, right? So we write this as this. That's the smallest key in the symbol table that's bigger than x. And the last two, so these are really the important ones. They look innocent maybe, but they're really powerful. Rank of a value is the number of keys in the symbol table strictly smaller than x. And select is give me the kth smallest. Because I used k for key before, I'd like to make this I. This is and it's just a name. And think about select really like an index into an array. Select is the very same thing as saying A of I. I want the ith position in an array. You can use select to get the ith entry in a binary search tree in its left to right order. And that means you can use ordered symbol tables to create dynamic arrays, in the sense that you can insert arbitrarily at any position. You can add new elements, and you can still access the middle. You can do binary search. You can do all these things using calls to select. Now, select is not constant time. It takes logarithmic time. We'll come to it in a minute. But you can still use this to build things that behave like an array, but can grow at any point in time very flexibly. That's the abstract data type. So this is that's the ADT. And as before, you see it sometimes as ordered map, or all these other names that I listed before. The implementation is this. Maybe show just the tree for now. Is an augmented binary search tree where every node also stores the size of its subtree, how many nodes are in its subtree. So you see that the leaves always have 1, and then this one has 2, 1, 2, and this one has 4, 1, 2, 3, 4. You always count yourself. And that will help us to implement these operations. Before we do that, I want to ask you this question on Slido. If you take this tree and what is rank of 35? If you execute this query, what's the result? I want to briefly see if you are familiar with the operations and that it makes sense to move on. Okay, 5 people voted, so you need a little more time. I'll leave the tree here instead of showing Slido because you probably need it. Okay, 17, 18 people. I should probably have added an option. I'm confused, I don't know. There you go. Okay, 26. We've reached 37 before, so maybe I'll give you a minute. Okay, I think the trend is clear. Let me show this here. So, well, I can show the correct answer. Most of you have it. I'll discuss why in a second, but there was also a few people who were either confused or said didn't know. So it's worth discussing this again very briefly. So just remember, rank is the number of keys in the symbol table that are strictly less than the argument that you pass. So in our example here, rank is past this value 35. So x is 35, right? And now we have to count how many keys in the symbol table are smaller. And one way to do this is just naively, well, there's 1, 2, 3, 4, and then these are all bigger. But remember, we can project the keys down here. So here's the 35. And you have to count how many are in this range. That's rank, and that's 4. All right. Let me close the poll again. So caveat number 1, it's essentially 0 based. You don't count the 35. It's the 5th smallest in this tree, but you say the rank is 4 because we start with 0. 11 would have rank 0, right? Yeah, so the second comment is probably best shown on the next slide. So that's rank, and you can figure out how the other operations work similarly. Here on this slide, let me show the same example again. So we're looking for 35. Here I added again the projection down, and I added the visuals of an array. And now, if you do this, you see that actually rank is precisely the index in this array. Okay, so for every element, it's rank. If you call rank with the key of a node, you get this number. All right, 4 is rank of 35. Rank means go down and take that number. But how do we compute this? I mean, this was like human insight, and we looked at the sorted list. How can the binary search tree compute the rank? So let's see. First, we do the search path. So we go and find our element. In this case, the 35 was in the in the tree, so we found it here. Now, the rank is computed as follows. Whenever we go to the left, we do nothing to our rank. We start with r equals 0. Whenever we go to the left at a node, we do nothing. When we go to the right, we check how big is the left subtree. So we take this and we add to r this node maybe is called V. So we add to r the left subtree size. I'll just use this notation for that. V is this node, the 12. Left is its left child, and st is this subtree size that we have stored in each node. But we also add +1 because we went to the right. That means also the 12 is smaller than the 35. Here again we go left, so we do nothing. Here we go right. So again, we look at the left subtree, and that has size 1. And we also add the 28. So we have, at this point, r is 2. And once we go down here, r is 4, because we have added 1 and 1 for the node where we are. And if we reach the node that way, we leave r where it is. And that's the right answer then. All right, that's how you do rank. It's fairly easy if you have the subtree sizes. How can we do select? How can we find the element at position 4? Let's do the same one, so we get the same result. So again, select 4, it should just be, if this was the array, it would just be accessing the 4th position at this array, except that this array doesn't really exist. It's only imaginary. It's only in our illustration. We don't really have that in memory. But we would like to find the 4th smallest element. So what we do is we start at the root, and we're looking for rank 4. Now, if we look at the entire left subtree of the root, we know that we can find its subtree size if we go to the left child, and then take its subtree size. This 9 gives me the rank of the root. All right. Now I compare 9 is less than 4 is less than 9, so I have to continue on the left. I don't think I can easily duplicate the slide. That's maybe I can. Okay, so we know that 4 is smaller than 9, so we continue to the next one. So we're looking for rank 4. Now we do the same thing. We look at the left subtree, look at its rank, and that tells us the rank of 12 is 1. But 4 is bigger than 1, so we have to go to the right and continue here. Now here we have to be careful. We're as soon as we go into this subtree, we're cutting off these 2 nodes. So we have to adjust, instead of 4, we now search 2. You have to subtract the rank of the node plus 1. So we start with r equal 4. If we go left, we do nothing. But if we go right, we do r minus, we subtract from r this the size of this part that we skipped. So again, v left subtree size and 1 for this node. So we're now down to this part. And okay, this is not too messy, so maybe I'll just continue on that slide. We try to find the node with rank 2 in here. And so one more time, we look at the left subtree. That has rank 4. So inside of this tree, we have 4. It's all shifted by 2 now. So 2 is less than 4, because 4 is the rank of this node, minus 2. I know this is a bit confusing. I wonder if there's a nicer way to illustrate it. So we have to go left again. And we ask here, where is the node of rank 2 within this? You look into the left, there you find a 1. So this is rank 1 minus 2. 2 is bigger than 1, so you go to the right. Okay, now you have to adjust the rank again. Now we ask for rank 0. We subtract this one and we subtract this one. And then finally here, we look into the left subtree. It's null, it's empty, so that means the root has rank 0. And there we found it and return it. And that was the correct answer because we know that this has rank 4. That's in a nutshell how you do select in an augmented binary search tree. And that brings me to the summary. Here are all the operations that we discussed before. This slide should have been earlier. That's what we discussed. They're all bounded by the height. And construct is essentially given by doing n times the insert. Okay, so there was a question about the number below the node. The number below the node is not the rank, it's the size of its subtree. You can compute the rank of the node from it, but only in a top-down traversal. It's not explicitly stored in the node because you couldn't maintain it. Okay, I think we have to postpone the balanced binary search tree part to tomorrow. One thing I wanted to add here is, okay, now we have the, now I need to turn this off again. Then we copy the background. I want an empty page. Now I copied it before, sorry. Now there we go. I screwed it up. This is the page I want to be on. After that page, a new page, please. Sorry for the mishap. Just to stress again, each node stores its subtree size, not its rank, because you could not maintain the rank information upon insertions and deletions. But subtree size can be maintained. I don't want to go into the details of this. If you want to see this, it's in the book of Sedgwick and Wayne and in their videos. Basically, you can go through the insertion and deletion procedure and see that for the nodes on the search path, you can just increment or decrement their subtree sizes by 1. And that's enough to maintain the subtree sizes. Whereas it wouldn't work for rank. Maybe let me give you a very small example if you like. So suppose there's a really huge tree on the left. So this might go on for quite a while. And now we insert a new node here. Which node's subtree sizes have to be changed? There's a +1 in this node's subtree, and a +1 in this node's subtree, and a +1 in this node's subtree. But the subtree sizes of all the nodes in this big part over there don't have to change. Now, I should have drawn the picture the other way around. It's not too hard to get, so bear with me for just 1 minute and then I'll wrap up for today. This works just the same, except that I need to make the edge a bit longer. So that's doable. Suppose this would have been the picture. It's easy to insert this node and update the subtree sizes of these nodes, because remember, these nodes are on the search path to the insertion position, so we have to walk that path anyways. But if you were to update the ranks, all of these ranks change. You would have to go to all of these nodes and add 1 to their rank, because there's a new element inserted left of them. And that doesn't work. You cannot do this in logarithmic time. Whereas if you do the subtree sizes, you can do it and you can compute the ranks in a top-down traversal. That concludes the part on the ordered dictionary implementations with binary search trees. And we'll wrap up the remaining part of binary search trees tomorrow.